Okay, so we've got a little bit to cover today, so we're just going to hop into it and get started. We're going to do another one of those combustion analysis problems. We'll work through it together so that you have the notes. Okay, so here is the problem we're going to be looking at. So menthol, the substances we can smell in cough drops, is composed of carbon, hydrogen, and oxygen. A 0.1005 gram sample of menthol is combusted, and our two products are 0.28929 grams of CO2 and 0.1159 grams of H2O. What is the empirical formula? And then it gives us a little bit more information about the molar mass, and it says, what's the molecular formula? So if you want, the first thing we can do is just sort of write like a pseudo reaction. So we've got menthol, which is carbon with some sort of number. We don't know what it is yet. Hydrogen with another thing, and oxygen is a Z. We're going to combust this with oxygen, and it's going to produce, remember when we combust, we always produce CO2 and H2O. So we know what the sample's original mass was, correct? It's 0.1005 grams of this menthol thing. We know how much CO2 we produce, okay? So CO2, we get 0.2829 grams of CO2. And the last thing is we know how much water we have. 0.1159 grams of H2O. So if I want to get my empirical formula, I need to have moles of carbon, I need to have moles of hydrogen, and I need to have moles of oxygen. And even before that, I need to get the mass of carbon, the mass of hydrogen, and the mass of oxygen. Oxygen is always the last thing that you solve for, okay? First, we solve either carbon or hydrogen. We'll start with carbon. Remember, CO2 tells you how much, will eventually tell us how much carbon we have. H2O tells us how much hydrogen we have. So let's start with the CO2. So if I move this over a little bit, this is how much CO2 I have. So I've got 0.2829 grams of CO2. This system is always going to be the same. It's the same system we followed the last time we did a combustion. So the first thing is to go from grams of your CO2 into moles of CO2. 1 mole of CO2 weighs roughly 44 grams of CO2. Why do we need to get into moles? Because I want to go from this value over here to how much carbon, and all the carbon was consumed here. So I want to figure out how much carbon is in this molecule. I know the mass of the molecule. So in order to jump from the molecule into the individual amount, I have to be in moles. So from there, 1 mole of CO2 will yield 1 mole of carbon. Why? Because you have 1 atom of carbon in every 1 molecule. Final step is to get this back into grams. So for every 1 mole of carbon, this thing weighs 12.01 grams of carbon. Moles of carbon cancel, moles of the compound cancel, grams of the compound cancel. That's always going to be your combustion system. Grams of compound into moles of compound into moles of individual element, moles of individual element back into your grams. So when we plug this all in, we should end up with 0.2829 0.07720 grams of carbon. So we've found out how many grams of carbon we have. That's getting us closer to solving the empirical formula. Now we're going to do the same thing, but instead we're going to work towards hydrogen using our water mass. So my water mass is 0.1159 grams of H2O. First thing I need to do, just like I did here, get out of grams of the compound and get it into moles of the compound. So 1 mole of water, obviously we're not going to use the CO2 stuff down here, we use water stuff, is 18.02 grams of H2O. Now, for every 1 mole of water, I want to get out of water and I want to get to an amount of hydrogen because I just want to know how much hydrogen there is. 1 mole of H2O produces how many moles of hydrogen? This is the step that can throw people off. Is it 1? No, it's 2. We get 2 moles of hydrogen for every 1 mole of H2O. Why? How many hydrogens are in each molecule? 2 hydrogens for every 1 H2O molecule, okay? That's where that number is coming from. So up top, I'm going to put 2 moles of hydrogen on top, and I'm going to put a little asterisk here, because if you miss that step in the first one, since it's a 1-to-1 ratio, it won't mess you up. But if you miss it in the second step, it will throw you off. And then the last step is to get out of our moles of hydrogen. We don't want moles of hydrogen anymore. And we're going to get it into grams of hydrogen, 1.01 grams of hydrogen. That's just the molar mass of hydrogen. And I end up getting 0.01 299 grams of hydrogen. So now I know my grams of carbon, and I know my grams of hydrogen. How do I get my grams of oxygen? You don't have to do anything very complicated to get grams of oxygen. We know the entire mass of the molecule, and we know how much of carbon we have, and we know how much of the hydrogen we have. So we're just going to subtract it. So let's move this up a little bit. So we take our total molecules mass, or our compounds mass, which is 0.1005 grams, and this is, hello, my compound. And we're going to subtract our carbon, 0.07720 grams. This is carbon. And we're also going to subtract the 0.01299 grams. This is my hydrogen, okay? So I'm taking this value here, subtracting the 2 that you calculated. What I don't want you to do, and it really won't work out for you anyway, is to take, to try and like maybe go an easy way and take this number and subtract this number and this number. You will end up with a negative number. You know that you've got to do this step here and this step here. Get your CO2 into your carbon, your H2O into your hydrogen. So then we do a simple, that simple subtraction, and we end up getting 0.01031 grams of oxygen. Awesome. Now I have grams of carbon, grams of hydrogen, and grams of oxygen. This is where we can start working through the empirical formula system. So I'm going to take the mass of each of these guys. I'm going to write it fresh here. And I'm going to convert the mass into moles, because remember, your empirical formula is not telling you a mass relationship. It's telling you a molar relationship. So we've got grams of carbon, and I don't like that. So I want to convert it into moles.
Can I ask a question real quick?
Of course. Yeah. Hop in there.
Why didn't we do the big equation for the oxygen again? I think I missed you saying.
Why did we not use that big long system that we use for the hydrogen and the carbon? Because we're actually adding oxygen to the system.
Okay.
So do you see how in that original equation, we've got oxygen here, but then we add oxygen to combust it? So if I calculated how much oxygen I had in here and how much oxygen I had in here, it would give me this oxygen plus this oxygen.
Okay,
We don't want the oxygen added. We just want this oxygen. And it would be a total pain in the butt to do anyway. So just subtract. Yeah, find the carbon, find the hydrogen, subtract from the original to get the oxygen.
Okay,
good with that, Brooke? Okay.
Yes.
Cool. So we're going to divide by our molar mass, 12.01 grams of carbon. This works out to 0.0, oh goodness. Sorry guys. 0.00648 moles of carbon. Okay, now we got our moles. We got to do the same thing for hydrogen. So we've got 0.01299 grams of hydrogen. 1 mole of hydrogen is 1.01 grams of hydrogen. All right, the grams will end up canceling. And we end up with 0.01286 moles of hydrogen. From here, we'll do the last thing, which is to calculate our oxygen. So oxygen, we had, from subtracting, we had 0.01031 grams of oxygen. For every 1 mole of oxygen, it weighs 16 grams of oxygen. So we take our number and divide it by 16, and we end up with 6.444 times 10 to the negative 4th moles of oxygen, a really tiny amount, right? So this is the molar relationship. This many moles to this many moles to this many moles. The thing that we don't like about this is that it is a decimal and they're not whole numbers. So we want to get these into whole numbers. We want to preserve the ratio, but convert it to whole numbers. So the first way we can do that is divide everything by a factor of whatever the lowest number is, okay, the lowest decimal. So this is a small decimal, this is a small decimal, this is the smallest decimal. So we're going to take each one of those and divide it by that 6.44 times 10 to the negative 4. And I will make sure to post these lecture notes up on YouTube, hopefully right after lecture. I'll just get them up so that you guys can use them to study. So we're going to divide each one of these by the 6.444 times 10 to the negative 4, 6.44 times 10 to the negative 4. There's another 4 in there. So many 4s times 10 to the negative 4. All right, anything divided by itself is 1. So I have 1 mole of oxygen. We've got a 1 there. When I take this 0.01286 and divide it by the 6.44 times 10 to the negative 4th, I should get a value of 20. And then when I take the 0.006428 and divide it by the 6.44 times 10 to the negative 4, I get a value of 10. So now I know what my empirical formula subscripts are going to be. It's whatever these numbers are. If those happen to not be whole numbers, multiply it by something to get it into a whole number. So carbon has a base 10. Hydrogen has a base 20. Oxygen has the subscript of 1. All right. Because it's 1, we can just leave that out. So this is the empirical formula. The problem did say, hey, let me know what the molecular formula is. Right up here. Hey, what's the, if methanol has a molar mass of 156, what is the molecular formula? So in order to calculate your molecular, go back over there. In order to calculate our molecular formula, the molecular formula is going to be my empirical formula, which is 610H20O times some multiplier N. We need to calculate N. So N is going to be your molecular over your empirical. All right, molecular, remember the top value will always be given to you. So we have 156 grams, grams per mole. The empirical is something we calculate. So we're going to calculate it from the empirical formula. So we're going to take, what do we have? 12, a mass of 12 times 10, so 120 plus pretty much 20 plus 16, because I have one oxygen, and it ends up being, 156 grams per mole. So what does that mean? That means that the molecular formula is the same as the empirical formula, right? Because when I divide those two, I get a value of 1. So how much bigger is the molecular formula than the empirical formula? It's not bigger. It's the same amount. So for molecular formula, for this guy, it will be C10H20O. Samesies. All right. Any questions on where I pulled numbers from on that? And so that if you need to go back and rewatch the video for details, that's fine. But if there's a question on like where it came from, let me know. Fine tuning your skill, you'll have to kind of do on your own time.
What would a molecular formula look like if N equaled 2?
Okay, let's do that. So let's just say hypothetically, we'll write it down here so that it doesn't ruin the work we've already got. But let's say that N, we ended up coming up with a value of, or let's say the molecular mass, instead of it being 156, Brittany, it was 468 grams per mole. Okay. If it was 468 grams per mole, we would take the 468 grams to find our N, divided by, grams per mole, divided by the empirical formula's mass, which is 156 grams per mole. In this case, we end up getting a value of 3. So what do we do with that? We plug it in right here where we said, hey, molecular formula is equal to your empirical times N. So we just multiply all those values times 3. So I'll take this and I'm going to multiply by the C10H20O. It gets distributed out to each thing. We get C30H60O3. Great. All right, so we're going to leave combustion analysis and we're going to move into the last little bit of this chapter. It's not really a little bit, but the last part of this chapter, which is stoichiometry, which if you've baked ever and adjusted a recipe, you've pretty much done stoichiometry in some capacity. So when we look at a balanced chemical equation, let me open that up so it's a little bit bigger. Okay. When we look at a balanced chemical equation, like this one, for instance, 2H2 plus 1O2 gives us 2H2O. The molecular interpretation of that is 2 molecules of the H2 combines with 1 molecule of the O2 to give us 2 water molecules. That's also a mole level relationship or interpretation as well. So 2 moles of hydrogen gas combined with 1 mole of oxygen gas to give us 2 moles of H2O, water. So within every balanced equation, there is a built-in molar relationship. So there's a couple ways that I could write this as far as mole relationship. I could say, hey, for every 1 mole of oxygen, I need 2 moles of H2 to make it work. If I want to produce 2 moles of H2O, I need to have 2 moles of H2. Or for every 2 moles of water that I want to produce, I need to have one mole 1 mole of the O2. So these coefficients that we've balanced, and know that there's an inferred one here, are a molar relationship, or it's a built-in recipe. Just like if you're baking pancakes. I don't say, hey, we're gonna make pancakes. It's eggs plus flour plus baking powder. Every single person would have a different pancake, and most of them would probably not work out very well. We need to say something like, hey, 1 cup of flour for every 2 teaspoons, for every 3 cups of this will produce 5 pancakes. So this is the recipe we're gonna go after. And what's really cool about this is that if I give you a certain amount of like hydrogen gas, you could tell me how much water you can produce. Or if I give you, hey, I need 20 grams of water, you could tell me exactly how much oxygen you would need in order to produce that. So the flow chart for this is on the next page. And it's always going to follow this system when you're going through stoichiometry. You're going to have substance A. Substance A is where you're starting. Okay, I'm giving you something about the product. Then substance A would be the product. I want to know something about a reactant. You would go towards substance B, which would be the reactant. So it's grams to moles to moles to grams. Grams to moles to moles to grams, or grams of A into moles of A into moles of B into grams of B. How do we get from grams of A into moles of A? We just use the molar mass of our compound A. How we get from moles of A into moles of B, this step here is the new step. This is the stoichiometry. We use the coefficients from a balanced chemical equation to relate A to B. So in that last one, let's say we wanted to, what do we have? 2H2 plus O2 produces 2 H2Os. Let's say we wanted to, we had a certain amount of water and we wanted to figure out oxygen. The relationship would be for every 2 moles of water that I want to produce, I would need 1 mole of O2. I'm not pulling those numbers out of thin air. I'm literally just using the coefficient in front of it. So now you can hop around a balanced equation. I could give you a product and you can tell me how much reactant you need. I could give you a reactant and you could tell me how much of another reactant you need. I could give you a reactant, you could tell me how much product you would need or receive or whatever. So that's in the conceptual gist of it, is what stoichiometry is.
Why are you writing it as 1 mole of O2 instead of 2 moles of O?
Because we want to treat those diatomics as molecule packets.
Okay.
So and we'll go over that too when we're calculating, but when you do 1 mole of O2, if you're going to convert that, you want to make sure you take into account the mass of 2 of them as well. Okay, but treat it as a packet. If it's given to you as an O2, treat it like that. So so here's an example. We've got, here it says, how many grams of water can be produced from 1 gram of glucose? Now, a couple things to note, asking yourself, am I supposed to do stoichiometry? What am I doing here? If there's a balanced equation, use it. Okay, we're not just gonna put that there for fun. Other things, if I'm asking you about or giving you information about one kind of compound, this is glucose, but I'm asking you about something in a different compound, you're having to change into some other compound, it's going to be stoichiometry. All right, if I said, hey, I've got this many grams of glucose, how many moles of glucose is that? You don't need to pull stoichiometry out. But if I'm saying, here's some glucose information, I want to know something about water, you've got to use stoichiometry. So with the balanced equation, I see here's my glucose. So I'm just going to like circle my glucose and I want to get over to water. So I want to go from here and I want to hop over to here. I have 1 gram of glucose to start. The first step is to take the grams of glucose, just follow the system, grams into moles. So for every 1 gram of C6H12O6, we use the molar mass of the glucose, which is 180, and we just divide it by that, and those will cancel. The next step after that, now we're going to do the stoichiometry. The middle step is the stoichiometry. So what is the relationship between glucose and water? Look at the coefficients. We can see that for every 1 mole of glucose, I need, or I will produce 6 moles of water. Because there's a 6 in front of the water, there's a 1 in front of the glucose. So moving on to the next step, and it'll carry this over, I believe. Okay, so now we're moving into that second step. So this here is this first step. This here, this is the magic stoichiometry. This is happening, I'm sorry. This is happening right here. So we use the coefficients of the balanced equation to hop pretty much, or change from glucose into water. The last step is just to go, because the problem said, hey, I want to know grams, I don't want to know moles, is to take the molar mass of water to convert it back into grams. So the next slide will kind of show all of those together. Okay, so final step here is to, this slide is incorrect. It's not 180. The molar mass of water is 18 grams. So first step is to go from grams of A into moles of A. Second step is to go from moles of A into moles of B using stoichiometry. Third step is to go from moles of B into grams of B, just using the molar mass of B. Don't use the molar mass of A in B, and don't use the molar mass of B in A. What's up, Brooke?
Will it always give us the balanced equation, or will we have to find it?
Sometimes you have to balance the equation yourself, or it could give you a word problem, okay? But it probably would give you, I mean, it's a multiple choice, so you know, some of these problems can take like a really long time. They'll be broken up into a couple different things, a couple different options, okay?
Thank you.
So then you just run it through your calculator, and that's it. So in this case, you end up with 0.600 grams of water. That's how much water will get produced. So let's do one of these separate from here. Notes from over here. All right, so here's a problem that's also talking about glucose. We'll keep the same formula. We'll do the first one together. And then the second one I want you to do on your own. So for this first one, it says how many grams how many grams of water could be produced from 150 grams of glucose? So I'm given glucose. I want to find water. Very similar to the last one we did. The only difference is that our starting information is a little bit bigger. So we have 150 grams of the C6H12O6. First step is to get out of grams of A, compound A, and into moles of compound A. So 1 mole of compound A, 6H12O6, what did we say? It was 180, right? 180 grams of the glucose. Okay, that'll cancel. Next step is to use our stoichiometry. So we want to go from moles of glucose into moles of water. This is not a mass relationship. So sometimes people end up skipping this step and they just try and go directly from grams of one thing into grams of the other. You can't, you have to go into moles. So we can see that for every 1 mole of glucose, C6H12O6. How much do we get? We get 6 moles of our H2O. 6 moles H2O. Okay, final step is to take that, because it wants grams, is to go for every 1 mole of H2O, it's roughly 100, it's roughly 18 grams of H2O. Okay, so the moles of the water cancel, the moles of the glucose cancel, the grams of the glucose cancel. When we throw that in to our calculator, I had the work done earlier. Combustion stuff. We get about 90.01 grams of H2O produced. So I want you to do this second one. The difference with the second one, you're using the same equation, but you just are going from different things. All right, in this problem, it says how many grams of glucose are you going to get if you know a certain amount of, or if you want to produce a certain amount of CO2. So you're going from glucose over here, knowing something about CO2 over here. So you guys take, I'll give you 5 minutes to set that one up, 107. If you have any questions whilst working on it, ask me. Set up the same though. So you've got your A here. This is compound A. You're gonna go grams of A into moles of A, into moles of B, into grams of B. Always the flow chart you take.
Candace, I have a question.
What's
So
that?
I guess it's the middle step where you're transitioning from like moles of CO2 to moles of glucose. How are we figuring the ratio exactly?
Just look at the coefficients. So 6 moles of CO2 is related to 1 mole of glucose. Yeah, you just use the balanced coefficients. If we were to compare CO2 to oxygen, it would be a 6-to-6 ratio. In our case, it's a 6-to-1 ratio. Okay, so for the setup for this one, we're going to do this. We're going to have more practice with this with limiting reactant problems because this is just doing.
I'm having a real hard time understanding you. You sound like super robotic.
Yes, no, maybe so.
Still pretty bad. Is anybody else getting this too?
Yeah, okay, hold on 1 second. Let me see. How about now when I turn my video off? Is it better?
No, it still sounds the same.
Any better?
No, sorry.
Okay. Figure out. Stop sharing for a second. Still no good.
Still no good.
Okay, I'm end the meeting for all of us and then just sign back in. So we'll have 2 recordings. Just know that we'll have 2 recordings for this lecture. But meet me back here in a minute. Okay.